Alrighty. Well, this is actually take 2 of my previous video because the first one crapped out on me at the end when I tried to stop the recording. So I am now teaching to an empty room, and so when I ask a question out loud, it's being asked to nobody in particular. So I'm not going to hear any answers, and there'll be no one in class to hear. So, of course, I can't just let the video go because you guys in Mr. Goff's class need to know what's going on. So here we go. I'll just teach to an empty room. Anyway, so today what we're going to be talking about, if you can look there in your notes, is section 6.2. We're going to be talking about differential equations, continuing our discussion of differential equations, talking specifically today about exponential growth and decay, and what that looks like as a differential equation. You've already kind of discussed some growth and decay stuff in your pre-calculus classes at least, but we're going to continue that now, applying some calculus in there and stuff like that. Okay, if you don't remember differential equations, right? All right, we'll do like a quick brief review of the things we were talking about before winter break. Okay, a differential equation is really just an equation, okay, with a derivative in it, right? We've already kind of, seen these when we did like implicit differentiation. We ended up with x's and y's and dy dx's all mixed together in an equation, and that was really a differential equation, okay? Here, we have a very simple one in example 1. It's just x times dy dx equals 3. That's a differential equation. It's an equation because it's got an equal sign, right? And it's a differential equation because it's got a derivative mixed in there in that equation with our variables and stuff. Okay, the one main strategy that we have for solving differential equations right now is the strategy of separation of variables, which is where we, take our x's and dx's and our y's and dy's and rewrite them so that we separate them, okay? Separate them so that the y's and dy's are on one side, the x's and dx's on the other side, and then we integrate. Okay, and of course, integrating 1 dy in this case, we end up with y, integrating 3 over x dx, ends up with 3 natural log of the absolute value of x, and then plus c. Okay, keep in mind, right, this is the general solution to the differential equation. We then can use, our information here that y evaluated at 1 gives us 5, and so, use that to find the c value and so on. Just like we do when we, find the specific solution to a integral, same idea here. Okay, keep in mind, right, that when you do this integration here, sometimes you can integrate both simultaneously at the next step, like I did here, and so the plus c can just go, 1 plus c can go right there. But of course, if, the left, or if one of the integrals happens to be more complicated, right, so let's say I can integrate the left one, no problem, but the right one I maybe need to do a u substitution or something like that and still have some work to do. You need to put that plus c in as soon as you integrate, whichever side you happen to integrate first. If you integrate them both at the same time, you can just throw it on the right side, doesn't really matter. But if you integrate one side first, that's where that plus c has to go, okay? And then you can, move it around as need be whenever you finally integrate the other side. Okay, nothing too crazy here. I think the rest of this stuff was pretty, straightforward. It is similar, I'll say, as to that, so nothing too crazy. Again, the big reason why we go over a lot of this is because it's a popular free response kind of question here, okay, answering questions about it and stuff, so that's why we really want to make sure we have a good, solid grasp of the differential equations and things. It's a popular free response question on the AP test that you'll all be taking in May. All right, so back to where we were. Today's a pretty light day, thank goodness, right? Coming back from break. I know you guys have already had one day back, but it was, still a nice light day here. We just have a proof we're going to do. We're going to do 1, 2, 3, 4 examples, okay? And that's really it. So I'm going to try and go through these pretty quickly here. You guys can pause as need be. Of course, you can also go back and watch the video too if I happen to go too fast for you. But yeah, so here we go without further ado. All right, so one of the more common applications to differential equations is modeling growth, especially in the field of science, okay? In many applications, the rate of change of a variable, y, of course, rate of change of a variable, y, we would know that as the derivative of y, now that we have calculus and stuff, right? The derivative of y is proportional to the value of y. Okay, so if y is a function of time, the proportionality can be written as dy dt, that is the rate of change of y, is equals proportional to the value of y, k times y, where k is just a constant. okay, or also known as the constant of proportionality. K is the proportionality constant, okay? So again, this is just directly from this relationship right here. The rate of change of a variable y, dy dt, is equals proportional to the value of y, k times y. That's it, okay? If y is a differentiable function of t, such that y is greater than 0 and y prime equals k times y. In other words, if we have this situation, okay, because isn't y prime equal to k times y? That's the same thing as dy dt equals k times y. If that's true for some constant k, then the solution to this differential equation is y equals ce to the kt. Okay, y equals ce to the kt. C is the initial value of y, and k is the proportionality constant. If you recall, in the last section that we did, we had a problem that was like this. I feel like we did, where we solved it and resulted in that solution. But now I'm having trouble finding. Maybe not. Okay, something close to it, but not quite the same. So here's the proof then of how we can go from this differential equation to this solution of it, right? How we know that this, given this differential equation, this relationship between something's derivative and that something. So in other words, if you have a situation where the rate of change of something is proportional to that something, okay, then you know that you're going to result in this scenario, the solution y equals c to the kt. So again, let me just kind of show that to you here. So we'll start with dy dt equals k times y. Okay, in order to solve this differential equation, we have to separate our variables, right? So we'll get the y's and dy's to one side, the t's and dt's to the other side. So I'm going to multiply the dt over. Okay, we still have to move this y over, so I'm going to divide the y over. So we have 1 over y dy equals k times dt. The k you can leave or you can move over to if you wanted to. K you're just going to treat it like a constant, like it was a 3 or a 4 or pi or e. It's some constant number. Okay, so now we have our y's and dy's on one side, just our dt on the other side with a k there. So we'll integrate now. Okay, what is the integral of 1 over y? Right, I can't hear you, so I'm just going to go ahead and say it's the natural log of the absolute value of y. Okay, and the integral of k with respect to t. Again, I can't hear you, but hopefully you were thinking or said k times t, and then we'll put the plus c in there. Since I integrated, again, both of these simultaneously, I'll just put the plus c on this side here. Oops, I'm going off the screen. Okay, so now we're not quite done yet because this doesn't quite look like our goal there, right? But let's go ahead and solve this for y. So to eliminate the natural log, well, what cancels out natural log? Okay, yeah, e. So we'll do e to each side there. The e and the natural log cancel out. We're left with the absolute value of y equals e to the kt plus c. Okay? Now, that absolute value, I know that can kind of like cause us some confusion or some uncertainty here. How do we deal with that? Well, in this particular case, we don't need to worry about the absolute value anymore. We can drop it. Why? Well, if you go back up here to this stipulation, if y is a differentiable function of t such that y is greater than 0, y has got to be positive, so we don't need to worry about absolute value. We can just make it y. Okay, so we can drop the absolute value. So now it's looking more like this, but we still don't quite have the same thing here, right? Remember, though, we have a sum in our exponent, okay? The sum in an exponent, that is a property of exponents that we can rewrite e to the kt plus c as e to the kt times e to the c. We don't normally go this direction, right? We don't normally take a sum and then break it up. We normally take a product like this and then say, well, we're multiplying two things with the same base, we add the exponents and result in this. But instead we're going kind of like the opposite direction. We're breaking up that sum into a product. Now this e to the c, well, remember c is a constant, right? And e is also a constant. So a constant to a constant, this thing is going to be overall a constant. So we're just going to rewrite that as a big C, e, and then to the kt like that. Okay, so that results in there's our e to the kt, there's our c, and there's our y equals c to the kt right there. Okay. So when you have a differential equation relationship that starts out with the derivative or the rate of change of something is proportional to that something, the result will always be this y equals ce to the kt. If you change this differential equation, then your solution will not necessarily be y equals ce to the kt, okay? So while now that you've seen this, differential equation results in this solution here, okay, just if this differential equation changes, then we won't necessarily have the same equation there. Okay, I know that maybe seems silly for me to say, or it seems obvious, but we'll see what happens later here. Okay, so looking at example 1, right, it says here the rate of change of y is proportional to y. Is that what we just talked about here? The rate of change of y, dy dt, is proportional to y, equals k times y. Again, that k creates the proportionality relationship there. It is exactly, okay, what we have right up here. And so we know, I'm just going to put a dot, dot, dot. We know what this integrates to be. It solves to be y equals ce to the kt. Okay, I'm not going to bother going through the proof again. You can just look back up here if you need to see it. Okay, but that is the result in the equation right there. I'll scoop this up now. Okay. Now, that's the solution, but of course we want to know ultimately what is the value of y when t is 3. Well, right now, if I were to plug 3 in for t and I wanted to solve for y, I have a problem, right? Plugging in 3 for t here, I don't know what k is, I don't know what c is. And so we can't solve for y without first figuring out what c and k are and then plugging in 3. So, how can we do that? What other information do we know about this curve? Well, we know when t is 0, y is 2. So, we'll put in, I'll say use t equals 0, y equals 2, like that. Okay, so we'll put 2 in, ce to the k times 0. 0 times k is 0, e to the 0 is 1. 1 times c is c, so c is 2. Okay, and so we get y equals 2 e to the kt. Now, of course, this shouldn't surprise us, right? What do we know c is in this scenario when we're talking about this kind of particular differential equation, y equals c to the kt? C, remember, was the initial value of y. Well, when t is 0, when t is 0, y equals 2. That means 2 is the initial value. So it wasn't even really necessary for us to solve here. We could have just plugged the 2 in for c, since we know at the initial point 0, when time is 0, the y value is 2. So we could have just plugged 2 in. Okay. We're not quite done, though. We still have to solve for k. So now what will we use? The other point there. T equals 2, y equals 4. So we'll use t equals 2, y equals 4. Again, I'm writing this use t equals 2, y equals 4. I'm putting that in the notes here just so you can have that note for yourself or whatever. You don't need to write that down when you're actually showing your work. Not necessary. Okay, just plug it in and stuff. Okay, so 4 goes in for y, 2 goes in for the t there, and now we solve. Okay, we want to get the k value, right? So we want to get k by itself. Well, the first step here, we'll divide both sides by 2 to get rid of that coefficient there. So we get 2 equals e to the 2k. How do we cancel out e? Right, natural log of 2 equals 2k. Okay, and then to finish off solving for k here, I'll multiply both sides by 1/2. So we have 1/2 natural log of 2. Okay. Remember that according to your logarithm properties here, right, this coefficient of 1/2, what could we do with that 1/2 coefficient in front of a natural log? Where can it go? Okay, so hopefully you remember that that 1/2 coefficient can become your exponent. Okay. If you don't remember that, right, you should blame your pre-cal teacher, unless your pre-cal teacher was me, in which case I'm blaming you. Just kidding, don't do that. Okay, but do remember that that is what you're supposed to do there. Natural log of 2 to the 1/2, or you can leave it as 1/2 times natural log of 2. Either one's fine. We'll plug it back in. Okay, and now we'll have the t there. Okay, and then we'll evaluate. So we want to now find the value of y when t is 3, so we'll just plug 3 in like so. Okay. This is the point where you want to get out your calculators and actually try and type this in to make sure that you can evaluate this accurately. Okay? Calculator is only as powerful as the person using it. So it's important that you can relate to the calculator what you want it to do. So I'm going to type in this right here and hopefully get a nice decimal answer here. Okay, I get about 5.657. Okay, so hopefully you got something similar to that, about 5.657. Of course, if this is a free response question, you may stop right here. Okay, if it's multiple choice, you can even stop there. If that's the answer, of course, they might give you the decimal, so just make sure you can get the correct decimal answer there. All right. Questions on any of that? Just kidding, I really can't help you. If you want to get some help, though, I mean, you can seek Mr. Widmeyer, me, out, for set or something like that. I'll be happy to, pull you in. Oh, right, we don't have any set this week anyway, so Mr. Goff will come back. Well, I'll be available before school or after school if you really want some help. I can do that. All right, but again, there's no set for the rest of the week, so yeah. Anywho, if you do have questions, though, again, please feel free to stop by my room. It's A101. It's down by next to Mr. Thompson's room. Okay, next to Mr. Weiss's room too. Okay, near Mr. Miller, Mr. Lillard's room. So anyway, moving on. Example 2 here. Okay, the rate of change of v. Okay, rate of change of v is proportional to the quotient of the square of v and the square root of t. Okay, so right. So this is one of those problems. We don't need to take we don't need to solve this differential equation right here, right? We know that this is going to be y equals ce to the kt, right? No, it is not y equals ce to the kt. Okay, why not? It's one of those problems. We're in here. We're talking about the rate of change of v, and it's proportional to something. Right, it is. But let's read carefully here what it is proportional to. The rate of change of v, so dv dt, equals proportional, so a k, to the quotient. Quotient means what operation? Yeah, division, okay, of the square of v, so v squared, and the square root of t over, I'm going to write that as t to the 1/2 as opposed to t square root of t like that. We'll make it t to the 1/2. That is your differential equation. Does this look like this? No, it does not, right? This is the rate of change of y is proportional to y. This is the rate of change of v is proportional to the quotient of the square of v and the square root of t. Okay? Since this differential equation is not the same as this differential equation, the solution to this differential equation most likely will not be the same solution as this differential equations. So that means we have to do this the long way and actually separate variables and then integrate. Okay? So, I'll move the dt over. Okay? I need to move the v squared over, so I'm going to divide both sides by v squared. So I get 1 over v squared equals dv. Whoops. Times dv. Sorry. I'm going to, again, divide the v squared over. So it's 1 over v squared dv equals k times 1 over t to the 1/2 dt. Okay, 1 over v squared is the same thing as v to the negative 2. 1 over t to the 1/2 is k t to the negative 1/2 dt. Yeah, it's more helpful to rewrite it as the negative exponents as opposed to leaving them in the fractions like that. Okay, the integral of v to the negative 2, is that natural log? The integral of v to the negative 2, is that natural log? Answer here is no, right? Natural log is the integral of v to the negative 1. V to the negative 2, you just use your power rule here. Okay, so integrating that, you get v to the negative 1 over negative 1 equal to, and then the integral of k times t to the negative 1/2. Again, k is a coefficient, so just integrate t to the negative 1/2. Again, this is the power rule. Add 1 here, so you get t to the 1/2 over 1/2, k in front, and then plus c like that. Okay, so let's kind of rework this here. This is going to end up being negative 1 over v equals, dividing by half, same thing as multiplying by 2, so 2k t to the 1/2 plus c. Okay? So there is our solved differential equation. Notice it does not ask that we isolate v. We don't need, it doesn't say solve for v in terms of t here. So we don't need to get v by itself here. Okay, we can just leave it as it is. If you want to solve for v, it's not wrong, but it's not necessary. Okay, the directions do not say solve for v in terms of t, so we don't need to get v by itself. We do, though, need to find the value of v when t is 3 eventually here, so we'll have to do some work. Okay, so if t is 0, v is 3. So we'll plug in 3 for v, so negative 1 over 3 equals 2 times k times 0 to the 1/2 plus c. Okay, we multiply here, 0 to the 1/2, 0 times k, 0 times 2, 0. So it's 0 plus c, so c is just negative 1/3. Okay, please, again, take the time, even though I know 0, this is an initial condition, okay, and quite often the c ends up being just that number right there, 3. Please actually take the time and convince yourself that is the case. It won't always be so. That c value will be exactly the 3 right there for the initial condition. It won't always work that way, okay? So please make sure that you take the time and just work it out to find your c there, okay? You can take a little bit more of a shortcut when you're doing these, differential equations here. You know that c is the initial value, so you can just go ahead and use the 2 there and stuff like that. But in these other ones, where it's a little bit different, I would be hesitant to do that and just solve for c. Okay, we've got our c value. We're going to subtract the 1/3 now instead of having the plus c. Are we done? Again, I can't hear you, so I don't know why I'm asking. But anyway, the answer is no, right? We still have to solve for k. And then we're still not done after that because we have to plug in for 3, t for 3 for t to get the v value. So anyway, let's use our next point here. T equals 1, v equals 2. So negative 1 over 2 equals 2 times k times 1 to the 1/2 minus 1/3. We now want to isolate the k here, so I'm going to have to add 1/3 over. Yes, we're going to have to add fractions. Negative 1/2 is the same thing as negative 3/6 plus 2/6, so negative 1/6 there equals 2k. 1 to the 1/2 is just 1, so I can just leave it as 2k. Divide the 2 over. K equals negative 1/12. So negative 1 over v, equals 2 times negative 1/12. I'll put the negative 1/12 in for k there. So 2 times negative 1/12, t to the 1/2 minus 1/3. Okay. So there is our relationship, and now we can finally plug in t equals 3 to get the value for v. So I'll do that right up here. So negative 1 over v equals 2 times negative 1/12 is negative 1/6. I'll go ahead and just simplify that. Times 3 to the 1/2 minus 1/3. I said t 3 to the 1/2 and then I wrote 1/3. So whoopsies, let me make that right there. Okay, so 3 to the 1/2 minus 1/3. Okay. So I'll try and simplify this a little bit here. Let's see, it's going to be negative square root of 3 over 6 minus 1 over 3. Okay, I got to get v. I got to isolate v though. So I'm going to multiply both sides by v. Like that. Okay, you can see again I just multiplied both sides by v, so it's going to be this quantity times v here. I want to get the v by itself, so I'm going to take this quantity, divide it over, and so I end up with v equals negative 1 over negative square root of 3 over 6 minus 1 over 3. Okay, you can stop there. That is, the final kind of solution. However, again, if it's multiple choice, most likely you won't have fractions within fractions as your multiple choice answer, so you do want to try and simplify out that fraction there. An easy way to do that is to kind of like multiply the top and bottom here by 6 in this case, right? So if you look here, right, you could get a common denominator, right? The common denominator here would be 6. But you can also multiply the top and bottom by 6. Okay, let me show you what I mean by that. So if I multiply the top and the bottom by 6, I end up with a negative 6 in the numerator over, and the 6 here in the denominator would distribute. Negative root 3 over 6 times 6 would just be negative root 3. And then 6 times a negative 1/3 would be negative 2. Okay, so that simplifies nicely. You could also factor out a negative here, and you could end up with just 6 over the square root of 3 plus 2. Right? Take a negative out of the denominator, so it'll be negative parentheses root 3 plus 2, and then the negative 6 and the negative would cancel out, and you end up with this. So lots of options here for simplification's sake. Okay? Important to see all that. Okay? So that was pretty intense. But similar principles to what we were talking about before. Separate your variables, integrate, find your C value, find your K value, and then finally plug in the T equals 3 and simplify. Okay. The calculus stopped right about here, right? The rest was algebra. So, all right. Example 3. Suppose an experimental population of fruit flies, I should say, grows according to the law of exponential growth. So this right here indicates that, okay, it's CE to the KT. Right? Exponential growth, that's CE to the KT. Okay? There were 100 flies at the beginning of the experiment and 300 flies after the 4th day. After how many days will there be 1,000 of the little buggers present? Okay. So again, law of exponential growth means we're talking y equals CE to the KT. Okay. We already know there's 100 flies at the beginning, so if you'll permit me here, I won't solve for C. I'll just take advantage of the fact that we know that we're starting with 100 flies, and so that means C will be 100 in this case. Again, if you don't believe me, you can plug 0 in for T, plug 100 in for Y, solve for C, you're going to get 100. Okay? So y equals 100 e to the kt. We're then going to use this second piece of information to find k. Okay, so 300 flies, that 300 flies is a y value. And then k, well, that's after the 4th day. Whoops. K times 4. Okay, again, 4 in for the t value there. And we're going to solve for k. So divide both sides by 100, you get 3 equals e to the 4k. Okay? And then how do we solve from here? How do we get rid of that e? Natural log. Okay, like so. And so then k is 1/4 natural log of 3. So our equation is y equals 100 e to the 1/4 natural log of 3 times t. We want to know when there's 1,000 of them present. So we'll plug 1,000 in for y, because now we know the population. We want to find the time, right? When, or after how many days. So t, we're going to solve for t here, the number of days. Okay, divide both sides by 100, you get 10 equals e to the 1/4 natural log of 3 times t. Take the natural log of both sides. One-fourth natural log of 3 times t, and so we'll then divide this quantity over. Actually, I'm going to multiply 4 over and then divide the natural log of 3. So I get 4 natural log of 10 over the natural log of 3 equals t. Bear in mind here, right, there is no easy way to simplify natural logs that are being divided. Right, natural log 10 divided by natural log 3, there's no easy way to simplify that, right? That's not like an easy way to, or there's no easy way to like simplify that, right? If we have if we have division inside of a single logarithm, that becomes subtraction outside, right? If we have multiplication inside of a logarithm, that becomes addition between two logarithms. But here we have division between two logarithms. There's no general rule there. So that's our value. Of course, we want to get a more precise value. You can type that into our calculator. And you should end up with approximately 8.384. Okay, and that's days. Okay. example 4, last one here. I want to let you guys go ahead and try and work on this one yourself. So if you want to like pause this example 4 here, I'll give you like a few minutes. Or obviously, you pause it. You give yourself as much time as you want. And then I'm going to start talking. Okay, I will assume that you have now unpaused the video and we are going to go over the answers for this. All right, so we're asked to let y equal f of t be a solution to the differential equation dy over dt equals k times y. So again, we can see here that this is the differential equation where the rate of change of y is proportional to y, because k is a constant there. Okay, values of f for selected values of t are given in the table above. Which of the following is an expression for f of t? So basically, we want to find which one of these is the solution to this particular differential equation right here using this information. So again, knowing that dy dt is k times y, we already know then we're going to have y equals c to the kt. We can plug in our information here. Using the fact that at time 0, f of t is 4, that's an initial condition. So we have 4e to the kt. And you might be tempted here to be like, man, look at that. Letter A, it's got 4 in front of it, right? None of these other ones have a 4, except for d, but that's not e to the kt. So, I mean, with that information, we are pretty sure it's got to be A here, but let's continue just to make sure, just for completion's sake. So let's plug 12 in for y and 2 in for t. Okay, so we get 3 equals e to the k times 2, and so then the natural log of 3 equals 2k, and so k equals 1/2 natural log of 3. And then plugging that back in, we get y equals 4e to the 1/2 natural log of 3 times t. Okay, and there we see the t over 2, right? The t can go out front here with the 1/2 t over 2, natural log of 3. There's a. Okay, again, if you have any questions, this video is posted to our Google Classroom. It'll be on YouTube. You can go back and look through any particular example that you like. If that still doesn't help you, feel free to, come see Mr. Widmeyer. Me, A101 is my room number. I'll be happy to answer any questions you might have. Let me see here what else I want to say. Fourth block students, I will try to come and see you at the end of each class, okay, to help get you any questions answered there that you might have. Block 2, you're kind of on your own, again, unless you come see me before or after school or something like that. Again, we have no set this week, so there's that. I did hear back from Mr. Goff. He said that he is doing all right, having a good time. Apparently, he has to, he's going to go camping. He probably told you he's going to go camping on Antarctica, but he has to, they're not using tents. He's going to be digging a hole for himself, and he called it digging his own grave. So anyway, he's hoping to come back with lots of pictures of penguins and whales and glaciers and ice and snow. In the meantime, you have to listen to boring old me. But anywho, we'll catch you again tomorrow, guys.